Alright, one last thing here. Last but certainly not the least, the idea of dimensional analysis. So far, most of the stuff we talked about today is something that you already know before for review. Okay, but this is something new to most people, this idea of dimensional analysis. Now suppose I give you a question. I say, I have two quantities, A and B. I want you to find C, which depends on A and B. Okay, I want you to find an expression for C, which depends on A and B. And you have no idea how to do it. You have absolutely no idea how to do it. Does that mean you're completely dead? You get 0%? Well, not necessarily. Sometimes, given the right circumstances, we can find a pretty good idea about what C is, how it depends on A and B, without getting into any physical details as to, the laws of physics that governs dependency of A, B, and C, and so on. This is why we study it in the very first chapter. Now, we don't know anything details in physics yet, right? And yet, I will show you with examples, we can actually find results that we otherwise would have to wait till physics 1B or even beyond to get. This is the so-called dimensional analysis. Okay, under the right circumstances, this works like a magical bullet. You can get the answer, almost the correct answer, almost the 100% correct answer, without getting into any real details. Isn't that wonderful? So, what is dimensional analysis? Well, first of all, the idea of dimension. It's related to the idea of units, but they're not quite the same. Let's look at an example. Lengths, right? There are different measurements for length, different units. I can have meters, inches, feet, miles, kilometers, all these, even light years. All these are units of lengths. They're different, okay? They're not the same units, but they belong to the same category. What category? They're all units of lengths. So in this sense, we say these are different units, but they have the same dimension. That is the dimension of lengths. All right? In dimensional analysis, I don't care whether we use meters, inches, feet, whatever, as long as a quantity has the same dimension, which is dimension of length or dimension of time, whatever. That's all I care. I don't care whether you use meters or centimeters to express that length. As long as it's length, that's all I care. So, what is the dimension of length? We call it L. Okay, that's the unit. That's the symbol we use. The dimension of time is denoted as capital T, and the dimension of mass is denoted as capital M. In mechanics, these are the three basic dimensions. All other quantities will have dimensions based on these three. For example, what is the dimension of the quantity speed? Well, speed is distance over time. All right. So the dimension of speed would be L over T, the dimension of length over the dimension of time. I can also write it down as L to the power 1 times T to the power negative 1. Okay, this is the dimension of speed. Let's say the speed is denoted as V. Okay, how do I denote the dimension of speed? Well, I put it in a bracket like this. Okay, this symbol means the dimension of this quantity V is length dimension over time dimension. So that's that. Okay, so that's the idea of dimension. So what is dimension analysis? Actually, very simple. If x equals y, then one necessary condition is that these two quantities must have the same dimension. Isn't that true? In other words, x, dimension of x, must be equal to the dimension of y. Okay? So this is the central idea of dimensional analysis. Of course, you say, hey, so what's the big deal? I mean, can you actually get something useful out of it? Well, yes, under the right circumstances. It turns out sometimes, in order to satisfy the fact, the condition that these two sides must have the same unit, we find that there are no other choices. Quantities must be combined in a certain way such that they have, the two sides, x and y, have exactly the same dimension. And that is how we do dimensional analysis. It's by equating, it's by demanding that the two sides of the equation have exactly the same dimension. Okay, you notice they don't have to have the same units. For example, here you can have 1 foot. Here you're going to have 12 inches. Obviously, 1 foot equals 12 inches. Feet and inches, they're not the same dimension, but I'm sorry, they are not the same units, but they both have the same dimension, that of lengths. Okay, so that's the idea of dimensional analysis. Now let's see. Let's look at some examples. In order to solve a problem with dimensional analysis, we're looking for a function, right? We're looking for a function. Suppose we're given several quantities, x, y, z, and so on. We're looking for a combination, a function of x, y, and z and so on, such that this function has a definite form, and that form is what we're looking for. Okay, for example, this could be the length, this could be the mass of something, and we put them in a function such that I get the speed or acceleration. Okay, so the whole idea is to try to find this function. Now, in order to find this function using dimensional analysis, let's be careful here. Remember, I'm assuming that we don't know anything else besides the dimension of these quantities. I don't know anything else. Okay, in other words, I cannot tell x away from y unless they have the same dimension. Think of a dimension as a tag, as a signature of this quantity. If x and y have the same dimension, then they may still be different physical quantities, but I don't have any way of telling them apart without knowing the details of their physics. If I only rely on the dimensions, then I must be able to tell them apart by assuming that they have different dimensions. Okay, so suppose I tell you, okay, a quantity depends on x, y, and z, but unfortunately x and y have the same dimension, both dimensions of lengths. Then, can we solve this problem with dimensional analysis? No, because I will have no way of telling x apart from y. Not only can they not have the same dimensions, but another case that's not quite possible is if this is area, x is area, y is length, I cannot use dimensional analysis either, because even though this is area, this is length, they don't have the same dimension, but I raise this length to the second power, I get area, right? In other words, the dimension of x, which is area, and the dimension of y squared, which is also area, cannot be distinguished. So I wouldn't know whether I should use x or should use y squared, because after all, x and y squared both have the same dimension, that of area. Okay, so I must make sure that these quantities, whatever is involved, must be separable with dimension, must be distinguishable with dimensions. All right, so here are the steps that I can take in order to find this unknown function. First of all, step number 1. You must identify which quantities can affect the result. Okay, say for example, okay, in order to find this function f, I find there are 3 unknowns, 3 parameters x, y, z. They can affect the result. These 3 and only these 3. That's the first thing you want to know. Which quantities affect? You don't even really know how they affect, but at least these are the quantities relevant. And secondly, check to see if x, y, z, and so on can be distinguished with their dimensions. Okay, if for example x and y are both lengths, no, you cannot do that because you cannot tell them apart with dimensions. Okay, you see, dimensional analysis is not universal. It's not universally applicable, but these are the conditions you must follow. First of all, you have to know which quantities are involved, and secondly, you make sure these quantities all have different dimensions. Okay. Now, if these 2 conditions are satisfied, we can actually start this process of matching the dimension of both sides. Okay. Let's say the quantity we're looking for. Let's give it a name. Let's say I have x and I have y. Okay, and the quantity that I want to find is capital A. Okay, it's A is a function of x and y. For simplicity, let's say just x and y. You can add z if you want to, no problem. And let's add a z. Okay, so this quantity A is a function of x, y, and z. I want to find the exact expression of this function. Okay, Now, how does one do that? Well, remember, this function has to be a combination of x, y, and z. They have to appear somewhere in that function. I just don't know how they do that. So you must imagine at the end, if you found that function, there must be some sort of operation in x, y, and z. It's a unique way of combining them together in order to find this function f, right? Let's see how we can put these functions together. You know, these quantities have different dimensions, x, y, and z. They don't have the same dimension. So is it possible to add them together? Let's say x plus y. Can we do that? Well, absolutely not, because two quantities with the same dimensions, you can add them together, no problem. One dog plus two dogs equals three dogs. Okay, but quantities with different dimensions, you can never put them together. You cannot say one dog plus two cats. That doesn't make any sense unless you say one animal plus two animals equals three animals. You see, quantities with different dimensions, you can never do addition and subtraction. Okay, now, so what do you do? Well, yeah, how about multiplication and division? Now that you can do. Okay, so in general, the way we combine these quantities together, knowing that they have different dimensions, is we cannot do addition and subtraction. We must do multiplication. So how about x times y times z? But of course, that is a little bit too narrow. It doesn't have to be exactly x times y. It could be x squared times y, or x squared times y to the power negative 3, right? That's possible. So in general, you're looking at x to a certain power, alpha, y to a certain power, beta, and z to a certain power, gamma. Remember, these quantities, alpha, beta, gamma, can be negative. Okay, it doesn't have to be positive. If it's negative, let's say beta equals negative 1. That means you're dividing by y. That's all. So that is the most general way of putting these quantities together. Okay, so basically you say a equals this, right? Now that's not exactly completed, because it is also possible that you may have a factor of 2 in front of it, factor of pi in front of whatever. In other words, whatever dimensionless constant. That constant has no dimension, just a number. Okay, let's call it c. All right. Dimensional analysis is powerless at obtaining that constant c. I would have no idea what that c is by looking at dimensions alone, because c has no dimension. In other words, it is totally invisible. Okay, remember, I'm tagging these quantities by using their dimensions alone. Okay, so dimension analysis does not give us the final answer in the sense that I don't know what c is. But even if I don't know what c is, if I can somehow find alpha, beta, and gamma, now, isn't that great? Because that allows me to find almost the entire result, just a constant c, up to a constant c, right? By matching simply the dimensions on the two sides. Okay, so that is the assumption. What do we do next? Well, remember, I must equate the two sides in terms of dimension, make sure they have the same dimension. So that means the dimension of A must equal to the dimension of this whole thing, right? Remember, C has no dimension, so it drops out. Okay, then that's x to the power alpha, y to the power beta, z to the power gamma. The dimension of this whole thing. Now, of course, if the dimension of x is L, length, then and if alpha is 3, okay, then it's L to the power 3, right? L to the power 3. And similarly with y to the power beta, whatever. I can, of course, rewrite this as dimension of x to the power alpha, dimension of y to the power beta, and dimension of z to the power gamma. Correct? Okay, now, even though I don't know the details how x, y, z affect this result A, I do know one thing, that is I know the unit of alpha, the dimension of x, dimension of y, dimension of z, and of course I know the dimension of A. So the next step is to write the dimensions of A, x, y, and z in terms of the fundamental or basic dimensions such as L, T, and M, so that the left-hand side will be a combination of L, T, and M to a certain power. The right-hand side, same thing, L, T, and M to whatever power. Okay? And then what do I do? Well, remember the two sides must have the same dimension. And also you realize that L, T, and M are totally independent dimensions. So if this side has M to the 3rd power, what do you think the M? What do you think should be the power of M on the right-hand side? it should be 3 because they have to match. If this side has t to the power 4, then that side, t must also raise to the power 4 because they have to match them. Okay, then I will get equations for alpha, beta, and gamma, which I can solve. That's how I find alpha, beta, and gamma based on dimensional analysis. Okay, that's the idea. Now, let's look at an example.